Hello guys, nice to see you. So today we are going to work with the topic which covers transformers. Hi, yeah, nice to see you. And filters based on capacitor resistor, capacitor inductor resistor. We'll see how it goes with time. I believe we will have some time by the end of the lecture, so probably we will also cover one topic which we didn't have time to cover last week, which is oscillations in RLC circuit. So we considered last week oscillations in LC circuit without resistors. So considered some ideal capacitor and inductance, or like in capacitor and inductor. And obviously we didn't have any attenuation of the amplitude of these oscillations of electric current and voltage in such a circuit. However, if we add resistor, the picture changes slightly. It starts to decay over time, and I believe it would be useful to consider this topic also. If we have time, we will do this today, since today's topics are not so big and there is not so much material to be discussed. Okay, then probably let me change the camera. Yeah, so we know that our electric network is built on the principles of alternating current signal system, and we have certain frequency of electric current or voltage, depends what we consider specifically in our power network. And in particular, in Kazakhstan, this frequency is 50 Hertz. Also, this is a standard for European countries. For United States is 60 Hertz. But the fundamental fact which should be considered is that these networks are working with AC current. So it was also mentioned earlier that it's necessary to operate at very high voltages in order to transmit electric power along large distances. So in order, like, since power which is delivered to a resistor, or in other words, Joule-length heat which is dissipating at the resistor is proportional to I squared times R. So in order to minimize energy losses, we need to reduce resistance. Obviously, we need to make these electric power lines of highly conductive metals with large cross section of these wires. And also, even more important, because here we have second power, we need to reduce electric current as much as possible. In order to transport equivalent amount of electric power, we obviously need to operate at very high voltage. So This high voltage is good for transporting. However, it's not good for generator. Usually they work at lower voltages, maybe like tens of kilovolts. Then it's step up with a transformer, a special device which can increase voltage, AC voltage, up to hundreds of kilovolts. Once it transmitted and then step down again to 10 kilovolts, distributed to some substations. And when we deliver it directly to the consumers, obviously we need to operate at lower voltages, which are much safer. So in European Union, also Kazakhstan, this voltage is 220 volts, and in United States is 110 volts. So we definitely need to use a cascade of these AC transformers in order to get eventually to realize this low loss transport of electric power along large distances, and then safe operation at the final consumer place. So transformer is a device which consists of two coils, those primary and secondary coils, and some ferromagnetic core. So let us show schematically a transformer. So this is our first coil, and we have this ferromagnetic core, which is usually made of iron. And in order to reduce this so-called eddy currents, it's made of laminate, so it's kind of laminated. So it's made of plates of iron, which are glued together but isolated electrically from each other. That makes such sandwich structure, makes possibility to reduce energy losses. And then we have the secondary coil. So first, this primary coil has N1 turns. Secondary coil has N2 turns. Then we have some potential difference, like voltage delta V1. Here we have delta V2. The role of the ferromagnetic core or iron core is to realize conditions when all magnetic field lines which go through primary coil also go through secondary coil. So of course there are some losses. However, the ferromagnetic feature of this core means that it enhances quite a lot the magnetic field inside, and this core is located in the interior part of both coils, coil primary and secondary coils, and that means that with very good approximation we can claim that magnetic field flux through primary coil is equal to magnetic field flux of the secondary coil. So that is very important, and that will help us to derive a simple equation which relates this voltage delta V1 with voltage delta V2 at primary and secondary at terminals of the primary and secondary coils respectively. So we can write based on the Faraday's law that voltage 1 is equal to minus N1 times rate of change of magnetic field flux. So we have dFB over dt. So assuming that a magnetic field flux through primary and secondary coils is equal, so we can write delta, actually like phi B1 is equal to B2, and this is equal to just FB. We can write similar equation for the second voltage delta V2, which appears at the terminals of the secondary coil. So delta V2 is equal to minus N2. And here is the same derivative because magnetic field flux is the same. So dFB over dt. Now we can solve for this derivative in both cases and equate two equations. So we will get delta V1 divided by N1 is equal to delta V2 divided by N2. Or in other form, which is more convenient, we can express the relationship between delta V1 and delta V2. So let's say we want to determine what will be the voltage at the terminals of the secondary coil, and that will be N2 divided by N1 times delta V1. So we see this very simple equation, which really describes and explains how AC transformer operates. There are three options. Usually two are very common. One is used in some specific cases. So option one, we have N2 larger than N1. And this is so-called step-up transformer because according to this equation which we derived, we see that delta V2 is larger than delta V1. So in order to increase voltage, for instance, when we go from the electrical generator towards this high voltage power grid designed for transmitting electric power along large distances, we want to increase voltage. And in this case, we need to use a transformer which has more coils at the secondary, more turns at the secondary coil in comparison to the primary coil. And it will be directly proportional, the ratio between voltages and number of coils. So second option, which is also quite common, is when N2 is smaller than N1. So in this case, delta V2 is smaller than delta V1. So this is so-called step-down transformer. And again, widely used because we need to go from this very high voltage in the power grid for transporting energy along large distances to some small voltages which can be delivered to consumers. However, there is the third option, and you may already consider this, that N2 is actually equal to N1 and delta V2 is equal to delta V1. So this sounds a bit strange, because why then do we need to use this transformer if it technically does nothing besides losing some energy, because efficiency of these transformers are from 90 to 99%, depends on construction and also frequency. That's another big important parameter. The higher frequency, the smaller and more efficient transformers. But this we will not discuss in details here. So this is so-called division transformer, which just divides two electric circuits and creates some gap, so there is no direct electrical contact between two circuits. However, we don't change voltage, and sometimes such devices are used in order to increase the reliability and stability of electrical, the quality of the electric power which is delivered. That could help to avoid some spikes in voltage, which could be because of different reasons generated in the network. Such isolating transformer could help to avoid certain very short but dangerous for different equipment spikes in voltage. So it works like some primitive stabilizer of output voltage. Not common, but definitely used in certain applications. So just keep in mind that such AC transformers also exist. So now we assume that we have some ideal transformer, so we don't lose any electric power, which for some examples of AC transformer is quite close to reality. So performance, like efficiency, could be quite high, up to 99%. So we can write that the power which is delivered to transformer from the side of primary coil, which is the product of current and voltage, is equal to the power which can be delivered to some load resistor connected to the secondary coil of the transformer. And again, it is defined by the product of electric current and, sorry, here is I2 and voltage in the secondary coil. So based on this equality, we can express, proceed a bit further. So now we, let's say we have some transformer and secondary coil is connected to some resistor, RL, let's call it. So current in the circuit, which is created by secondary coil and this resistor, I2, will be equal to the voltage in the secondary coil, delta V2 divided by RL. It's load resistor. At the same time, we can express some this current in the first primary coil as delta V1 divided by some R equivalent. So this is some equivalent resistance which will be determined by the ratio of number of turns in each coils and also load resistor. So why equivalent? Because here we don't have any resistor connected, so just voltage applied to this primary coil, but this current will be a function of load resistor. The current in the primary coil will be a function of load resistor attached to the secondary coil, and also on the ratio between a ratio of number of turns in each of these coils. So let us try to get expression for this equivalent resistance of primary coil. So we can write that I1 is so I1, this is delta V1 divided by R equivalent. And from this equality here, I1 is expressed as I2 divided by, times delta V2 divided by delta V1. Now we can, so this comes from here. Now we can substitute I2 with its expression, delta V2 divided by RL. So then we get delta V2 divided by delta V1 times delta V2 divided by RL. Okay, so we know that from previous slide that this ratio delta V2 divided by delta V1 is equal to the ratio of the number of turns in each coil, N2 divided by N1. So we can continue and write that I1 is equal to N2 divided by N1 delta V2 divided by RL. Now we need to go from delta V2 to delta V1 because we want to determine equivalent resistance in the primary coil. So we need to deal with the voltage at the primary coil. And again, we know that delta V2 is can be expressed as N2 divided by N1 times delta V1. So now we substitute instead of delta V2 this expression, and what do we get? It will be N2 over N1. Again, we have N2 over N1 delta V1 divided by RL. And this is N2 divided by N1 square times delta V1 divided by RL. Again, this can be expressed in terms of equivalent resistance. That will be delta V1 divided by RL. equivalent. From here, we can express value for equivalent resistor. So it will be 1 over R equivalent equal to N2 divided by N1 square times 1 over RL. And finally, for R equivalent, we get N1 over N2 square times RL. So this is equation for equivalent resistance of the primary coil, which is a function of N1, N2, and the load resistor. And that is kind of interesting, since the resistors of the input has some feedback with the resistance of the output, and also with the ratio of this number of turns in each coils. Means that by varying the load and ratio of turns, we can change the input resistance and match input resistance with so-called input impedance matching, match input resistance of some circuit with the signal generator resistance. That means that we will get the highest signal possible, because we know from previous lectures that the maximum power delivered to the load resistor will be in that case when the internal resistance of battery or power source is equal to the load resistor. In this case, the delivered power will be maximum, and sometimes we want this to be maximum. For instance, in some audio electric circuits, when we want to get maximum signal, audio signal, to get the highest possible quality. Okay, so with this, we are done. Now let us consider rectifiers and filters. Maybe let me change, like share my screen. Okay, screen. So there are sometimes needs to cut certain frequencies from passing through electric circuit in order not to deal with them further, because they don't carry any useful information and can just cause some noise or misinterpretation of our results. So there are different types of filters. Let us consider them here. So there's so-called low pass filter. In this case, it allows only low frequency from 0 to some cutoff frequency to go through the filter, and at frequencies higher than this cutoff frequency, it stops it. So nothing is going through. So we can, if we are interested only in low frequencies up to a certain value, then such low pass filter is the device which will satisfy our needs. For instance, if there is another requirement, we can use high pass filter. So high pass filter is allows us to pass only high frequencies from some cutoff frequency to, in general, let's say like infinity, but obviously it's exaggerated, so to some very high frequencies present in the spectrum. But if we have frequencies lower than this, cutoff frequency, all of them will be stopped by this high-pass filter. And in this case, for instance, some noise generated from the electric power system with 50 or 60 hertz or some secondary harmonics of these frequencies, they will not show up in our some high precision measurement if we manage to design a high pass filter which will block all low frequency signals which are originated from this power network. And there is, since we deal with AC current in power network, these frequencies, which are 60 or 50 hertz, they are really quite annoying for different, for operation of different devices and should be stopped. Another thing, if we have some requirement to pass only signals within certain frequency range. So we have two cut, like low and high cutoff frequencies. And in that case, we should use band pass filter. We will block everything, all signals with frequencies lower than the low cutoff frequency and frequencies higher than the high cutoff frequency. Another option is band stop filter, when we need to pass everything besides some specific range of frequencies, which also defined by low and high cutoff frequencies. Then we let all signals pass through, but this particular band is blocked. So the most simple low pass filter is shown here. We have some signal going through with some input voltage. This signal, this current flows through resistor and capacitor connected in series. And then output voltage is actually voltage drop over the capacitor. So what happens here, if we have very low frequency, let's say we have DC, that is the lowest 0 hertz frequency. For the lowest frequency, we don't have any current flowing through this circuit because for DC condition, this is just open circuit. A capacitor, we have insulator between two plates. In this case, voltage is drop over this capacitor is equal, this output voltage is equal to input voltage because all voltage is dropped here. This is the circuit element with much larger resistance than resistor R. That's why if we consider at this plot a ratio of output and input voltage at low frequency, like close to 0, this ratio gives us unity. So they are equal to each other. However, if frequency increases, then resistance of resistor R, it's a constant parameter. It doesn't change with frequency. And we know from previous lectures that capacitance, capacitive reactance, this opposition of capacitor for AC electric current, decreases with increase of frequency. So capacitive reactance is equal to 1 over omega times C. So we increase frequency, this capacitive reactance decreases, and some current is flowing through the circuit. So now there will be division of voltage drops between resistor and capacitor, because not all voltage will drop over capacitor, since this resistance becomes smaller, and relative voltage drop over capacitor and resistor drops. So that also reflected here. The output voltage is the voltage drop over capacitor. So we see that is increase of frequency, this output voltage decreases. At some point, when frequency is very high, capacitive reactance will be very low, because omega in the denominator for capacitive reactance. And all voltage will drop on this constant resistor. In that case, there will be almost zero negligible voltage drop over capacitor, and our output voltage will be negligibly small. So it will go to almost zero. That's why such electric circuit can operate as a low-pass filter, and it will allow low frequency signal to pass through. So we see in low frequency range, we don't see any reduction of the signal. Input, output is voltage is, they are equal between each other. However, if we have some high frequency signal, which is transmitted in addition to low frequency signal and is kind of parasitic one, it will be just filtered out by this low pass filter, and output voltage will be zero for high frequency signal. Means that only from 0 to some cutoff frequency will pass, and from cutoff frequency and higher will be neglected. So this is the principle of operation for very like the most simple RC low pass filter. Another topic which we would like to consider today, actually we don't have much time left, let's discuss this topic, is the rectifier. So we know that it is necessary to rectify AC current in order to power most of our electronic devices. We have these power supplies where we have input 220 or 110 AC voltage. Then we have a transformer which step down the voltage to, for instance, I don't know, 9, 6 volts, depends on the device which we want to power. And then the voltage matches. However, it's still AC. It has this positive and negative during each period. Half of the period voltage is positive, half of the period voltage is negative. So we need to solve this problem somehow. The easiest solution is just to connect a diode in series to the secondary coil of the transformer, and that will help in order to cut off the each half of the period with negative voltage or negative current. So a diode is such two-terminal electric circuit component which possess some asymmetric conductivity. At certain polarity, which is called forward bias, it conducts current. At certain polarity, which is like at opposite polarity, which is called reverse bias, it doesn't conduct current. So its resistance is polarity dependent. So in that case, it will be working, however, not very efficiently, because what will happen, we have a sinusoidal signal up and down, but it will pass only one polarity. So it will go here up, then here will be 0, here again up, here 0. So it will be just so-called half-period rectification, which means we will lose power, and our output will be quite with, it will not be, it will be so-called pulsed DC, but we want to have it smooth. So in order to make it smoother, we use so-called diode bridges. So we have 4 diodes connected in this way. And in this case, doesn't matter what will be polarity of the AC power supply. We will have always the same direction of electric current flowing through this load resistor. For instance, so here we see, let's say, polarity first half of the period, we have plus and minus. So this arrow of the diode shows where current will flow at this, when we have plus here and minus here. So current will flow in this direction. So this diode is closed, you see. So here we have plus and here minus, and this polarity is called reverse polarity for this diode. So current can flow through this this diode, then it goes through the load resistor. It comes back here to the diode bridge, and it flows through diode 2. So it flows through diode 1, through load resistor, and through diode 2, comes back to the power supply. So that is our half of the period here. Now we change polarity. It's second half of the period, and plus. So here is already minus, here is plus. So we go from plus. This diode is closed, but diode 3 is open. So current goes through diode 3, through resistor, comes back to the diode bridge, and again here diode 4 is open. So it let current flow back to the power supply. We see during both of half of the periods, electric current direction through load resistor is the same. So it means with such diode bridge, we can rectify both periods of, both halves of the period of AC current. And this, instead of having this sinusoidal signal with positive and negative, it flips over this negative part, and we have such pulse DC current. DC because it goes in only one direction. However, these pulses are not good for our electronic devices. We want to get rid of them, and the option to make it smoother is to connect in parallel to the load resistor a capacitor. So when voltage here increases, we will charge capacitor. When voltage decreases to 0, this capacitor will be discharging, and that will keep up the current in the circuit. So instead of going down, this current will still flow in the circuit. And again, when we go to 0 and our capacitor is fully discharged, we start to charge it again. So that's why such approach allows to go through sinusoidal signal to quite smooth pulse DC current, which is already applicable for power different electronic devices, and it can be smoothed quite a lot. So it's not exactly such a DC current which we can get from a battery. However, it's quite close and definitely can work with electronic devices. So these are the basic principles of this transformer, rectification, and filters. These are like key electronic components of each power supply. Doesn't matter where you consider a power supply, for charging your phone, for charging your laptop, like power supply in the desktop, or some other more powerful consumers of electricity, where we have this transformation of AC current from the power grid to DC pulsed current. These components, transformer, rectifying bridge, and RC or RLC, high and low pass filters, they are always present there, because if you want to get high quality DC current as output without any parasitic signals from low and high frequencies, that is necessary to apply all these three components, realized in different ways. Somewhere it's very simple, somewhere it's very sophisticated. It all depends on the requirements for the quality of this DC current at the output. Okay, so pretty much we are out of time. Thank you very much for attention. Any questions? So I would like to highlight that next week, this is like a spring break, and so we don't have lectures. Please don't forget to read the textbook, repeat the material, also practice solving problems. So we will continue in a week, when we will start with electromagnetic waves. So it's Maxwell equation, and discuss electromagnetic waves, which will be the last topic discussed in the frame of our course related to electromagnetism. And next part, so in a week after spring break, we will start to work with optics. Okay, then, thank you very much for attention again. Wish you good spring break, relax a bit, gain some energy, don't collect corona, and take care, be healthy, and see you after the break. Bye-bye.